So last time we discussed, we learned two data structures. What are they?
Stack and queue.
Yeah, stack and queue. So last time we learned stack and queue, and we said that both of them are pretty much like arrays, but the only thing is that we don't use all of the spaces in them, which we just use a portion of it, okay? We just use a portion of it. And so that it leaves some buffer space, and just in case that we want to insert a new element, we can do it pretty quickly. For both of them, the insertion and deletion complexity are 0.1. So meaning that if you want to insert an element, the time performance does not depend on the number of elements in these data structures, which is a very good property compared with arrays. And here we say that that even though these two data structures are very similar to each other, so they still share they still have some differences. So in terms of the policy, what is the policy for stack?
Last in, first out.
Yes, last in, first out is for stack. First out is for stack. Okay, first out. So the element who comes in last will be able to get out first. So we said you can take it as the shelves in a supermarket. And so in this way, all the elements have to be in the first couple of places in a stack, and we only need to keep track of one variable named the top. So top basically tells us the index of the last element in the stack. Okay, so from the first space until top, we got values in the stack. So this is the stack. And then for queue, it implements a different policy. What is the policy of queue?
First in, first out.
Yes, first in, first out. So we say that you can take it as the waiting room. So whoever comes to see the doctor, whoever comes in the waiting room first is able to go to see the doctor first. And so also so we say so because of this, in queue we don't always use the first portion, so the left portion of the array. Instead, we can just use any portion of the array. And so we need to keep track of two indexes, which are head. So this tells us, okay, well, so the place of the first element in the queue, and then the other one is called tail. Tail points to the next available place, so that if you have a new value, it will be placed at here. It will be inserted at here. So so these are stacks and queues. And so today we're going to learn a new one named linked list. So here you can see that for both stack and queue, because they're still arrays. So if we take a picture, if we take this as the RAM or as the memory, as the physical memory of your computer, whenever you create a stack or queue, it is like this. So suppose that you say, okay, you want to create a stack whose maximum length is, let's say, 100. It will go to your memory and ask for a space, a consecutive space that as large as so it can hold 100 integers. So for example, if you are asking for integers and say each integer, one integer is like, in Java, one integer is 4 bytes, takes 4 bytes. So it will allocate an array. It will just ask the operating system to allocate a space as large as 400 bytes in your memory, and then all the values that you stored in the array are just consecutive. They're just next to each other. Each of them is just next to each other. Suppose that you are checking this value, and you know that on your right, just on your right, there is some other value. So this is how stack and queue and array works. I mean, so basically we need to store these values consecutively in memory, and and this can give us some trouble, because if you are asking for an array, so if you are not asking for 400 bytes consecutive space, instead you are asking for let's say 400 million bytes as consecutive space. And then if your memory, if the RAM in your memory is the RAM on your computer is relatively small, you may not be able to afford to allocate a space that or consecutive space that is as large as 400 megabytes. So sometimes we may have some spaces like some free spaces in the memory, like one megabyte over here and 2 megabytes over here, but we just do not have a consecutive space that is as large as 400 megabytes. And then in that case, you are not going to be able to successfully create the stack or queue because there's just so currently there is no consecutive space as large as that. So this is for example, this is something like if you have a really big family, let's say there are 20 people in your family, and so you are hunting for, so if you want to allocate all these 20 people in one house, then basically you need to for a, let's say, 18-bedroom house. And unfortunately on the market, there is no house that is as large as this. So in order to solve the problem, what you can do is that, okay, instead of just buying a house with 18 bedrooms, you can do this, okay? You can say buy an apartment, a 1-bedroom apartment for 1 people in your family, and then another 1-bedroom apartment. Okay, so these apartments may not be in the same building. They may not even be located on they may not even located on the same street. But the thing is that from the first apartment, you know the address of the second apartment, and then in the second apartment, you know the address of the third apartment. So in this way, you can just buy, say 18 1-bedroom apartments across different cities and across different streets, and so that you are able to allocate these people in your family. And so similarly in the memory, what we want to do is that, okay, so we want to create some scattered spaces. We want to create a data structure with scattered spaces, and from the first space we know we got a link to the second space. From the second space we got a link to the third space. So by following the link, you will be able to go through all the values that you want to store in the data structure. So actually, the data structure that we learned today is called linked list, and it follows this way. Okay, so linked list are basically consists of nodes, and each node can have usually have 2 pieces of information, like what kind of value that you want to store over here. So suppose that you want to store int, let's say 4, and then the second part is the link to the next node. So it has a link to the next node. Say here you want to store, you have another node. Say that here you want to store some value, say 8, and then it has the link to the next node. And from here, let's say you store another value 1, it has a link to the next node. So in this way, we don't store the values consecutively in an array. Instead, we basically follow this way. Okay, we store the values. We store the values in different nodes or in different regions of our memory, but still we are able, by following the links, we are able to go through all the values. Is that clear?
Yes.
Yeah.
Okay. So sorry, I forgot to open up my video, and this is the big picture of linked list. So different from it's not array anymore, and we basically store the values in some scattered places, and so in this way so we can manipulate the memory in a more efficient way, or so we don't have to always ask for a very large consecutive space. Yes, this is the big picture of linked list, and as I said before, so this is what I showed before. Okay, so basically for a linked list just consists of different nodes. So each node stores the value. We call it data, and then next is the pointer or is the address to the node after it. So you can take it as the address, okay? So, or yes, a link to the node after it. So here, giving all these nodes. So for example, here we want to store 4 integers whose values are 3, 10, 2, and 1, and we can scatter these 4 values in 4 nodes, four nodes, and then so each node holds a link to the next one. So and here say because the last node, for example, the last node over here, there is no node after it, so we just assign a nil to its next field. Nil means does not exist or nothing. So in Java, nil is null. It's just a keyword, stands for nothing. So do you know null in Java?
Yes.
Yes. So this stands for, it's basically constant. I think its value should be -1, and it stands for does not exist. So because after this node there was no other node, so the link is we assign now to its link or to its next field, meaning that there is nothing after it. So here, say giving a linked list of 4 nodes. Actually, we don't need to remember the address of all of them. For all of them, we don't need to remember their address. We don't need to remember where are they. Instead, we only need to know where is the first node. So as long as we know the first node, by following the link, we will be able to go through every node, or every value that we want to store in this linked list. This is the and actually for a whole linked list, even though it can consist of a lot of nodes, we only keep track of the first node, and we give the term called head. So for a whole linked list, we only need to keep track of the head, and then we don't need to worry about the rest of them, because the other nodes, because just by following the link starting from the head, we will be able to go through each of them. So this is the big picture about linked list. Any questions so far?
Yeah, real quick if I can. So
Sure.
let's say you wanted to refer to the data that says like 2. So would you like call the first, like would you call the head and then like say move over 2 spaces? Like how would you refer to that
Okay,
element?
cool. So the question is that, so suppose here we only know the head. How could we visit this node which holds the value 2? So here, what you can do is that you can create a node. Let's say we have we define a type, or we define a class named list node. What you can do is this: list node x will create a variable named x equal to the head. Okay, so at first we say x equal to the head, then we let x equal to x dot next. So with this line, with the first line, we basically have x over here, and with this line, with the second line, it's kind of like I++. We move the index 1 position to the right. So we move x. We assign. We basically let x move to its right place. Move to the node next to it, and next we just have x equal to x dot next. Again, we move it over here. So here we are at, so x is basically the node that holds the value 2.
Okay, understood. Also, if I can ask, what would be the advantage of using this over an array? Like, what would you say is the purpose of the linked list?
Okay, so the advantage of this data structure compared with the array is here. Okay, for arrays, you have to always allocate consecutive space in your memory. But the thing is that, okay, if you have a lot of, so when you learn the operating system class, when you take the operating system class, the thing is that, suppose here you are running different processes. Let's say you're having your Zoom, you're running the Zoom application in your memory, And then here you are running another one. Let's say you are running a video game, and then you are having so you are also running your Chrome, okay? And then you may have your Word or Eclipse open, okay? So Eclipse. So the thing is that, so for now, if you just want to create a space, you want to create a very large array, say whose space is as large as this. You want to create this large space, as large as this. The thing is that in your memory, there is no free space. There is no single free space that is as large as this one. So as large as this size, so that you cannot, if you want to create an array as large as this, you will fail, because your Java is going to tell you there is no free space as large as what you requested. But so the thing is that, so if we take advantage of all the small but available space in our memory. Let's say we allocate a part of the array over here, or a part of the values over here, and a part over here, and a part over here, and a part over here. You will still be able, your request is still able to be requested, are still able to be requested. The only thing is that they are just not at a consecutive space. So these values are not consecutive. So after after the first block of the values that we just allocate, we need to know where does the second block start. So we create so at the last position of the first block, we hold a link to the next block, so that after you iterate the values right over here, you can go to the next block to iterate to visit values. Similar here, we create a link. So basically, this is the reason why we use linked list, because it allows us to store values in discrete or in scattered places.
Gotcha. Understood. Thank you.
No problem.
Hey, Professor.
Okay.
I actually have a question.
Sure.
I know that you said that we only need to know the first data structure, so the head.
Yes.
And then, so you don't need to know the last one, because when you have to point like null to the last index, or not index, but the last structure, I guess.
Mm-hmm.
So
okay.
Wouldn't you have to know what it was, what the last item is?
Okay. Cool. So okay, we got a very good question. The question is that, so since we only know the head, so if we want to go over all the values in the linked list, how do we know if we already reached the end of the linked list? So because for arrays, it's going to be pretty simple. We just, let's say for integer I, if we are talking about Java, okay, let's say if we let's talk about Java, okay. If in Java you have an array, and so initially you use the index as 0, and I is less than the length of the array. So as long as I is less than the end of the array, you basically know that so you are still inside the array. You don't reach out of the bound, right? You don't go out of the bound. But for linked list, how do we know that? And here probably you can say that the biggest difference between the last node and the other node is that the last node, the next field of the last node is new, whereas for the other nodes, their next field is basically a link or the address of the node next to it, right? So so let's say if now we want to go over every node inside the array, let's say first we have x equal to the head, and while x is not new, x equal to x dot next. So this is like, while x is not new, while you are not here, you are not at here, you are able to move it to move x to the right. So that in the beginning we have x here, and then we move to here, we move to here, and then we move to here, and then we stop. So x equal to x dot next is something like I++.
Okay, all right. Thank you.
No problem.
That's what we have to iterate over a linked list?
Yes. Yes,
Okay.
that's how do you switch over linked list. Since we already reached this deep, we're talking about the actual code. Let me share it with you. Okay, so let me share the scaling code that I provide for you to do the homework. So let me open up my Eclipse. Okay, so let's look at yes, this is the scaling code that I provide for you, DS. And so for you to do linked list, I prepared two files for you. This one is called linked list, and the other one is called list node. So list node basically defines what does each node have. So you can see here each node has 3 fields. An integer key, which key basically tells you what kind of values is stored in this node. A previous and a next, both of them have the type list node. So this means that previous is the link to the node before it, and next is the link to the node after the current node. Okay, so you don't have to touch this file, you don't have to manipulate it. You just keep this file as unchanged, and you need to manipulate your you need to do some edit over this file called linked list. So here you can see that for whole linked list, we only keep track of the head, and then so you need to implement 3 functions of linked list: the search, insertion, and deletion. So which we're going to talk about very soon. And then this is the one that so helps you to say convert the values in a linked list to string. So here basically what it does is that it iterates over the linked list. So here you can say that first we create a list node not named X, but it's named N. If you want, you can change it to X. But let me change it to X. So X, X is not. So it's easier for to understand. So basically, we want to use X to iterate over the whole linked list. So initially we have X equal to the head. While X is not new, we have X equal to X dot next. In this way, you iterate through all the nodes inside the linked list. And what we do here is that we basically concatenate the values stored in every node, in each node of the linked list to a string, and then we finally return the string. Okay, so so here I just want to show you how to go over a linked list. So you basically create a node which points to the head first, and then and in every step you just move this node one step further, one step to the right. Make sense?
Yeah, that makes sense.
Yeah.
Okay, sure. So I'm going to come back to my iPad. Okay. So there are different types of linked list. One of them is called a single linked list. So we call it a single linked list because every node only has a single link, which is the link to the node after it. So the other one is called a double linked list. So here every node has, so if we just look at this node, it has two links. One link to the node before it, and one link to the node after it. So and then so that's the reason why we call that we call this data structure double linked list. And the link before it, we give the name previous, PREV. This is what I showed in the scaling code I provide to you. And then the link to the node after it is called next. And so there so based on this singular linked list and double linked list, some people create a circular linked list. So that is by letting the last node, so link having the link to the first node. So in this way, we basically can iterate through the linked list in a circular way, and then we have double circular linked list. We rarely use circular linked list in practice. We mainly use these two. We mainly use single linked list or double linked list. So in our lecture, we will focus on this one. We will focus on double linked list, and this is the one that you are going to implement in your homework. So again, so this is the picture of a double linked list. So every node has 3 pieces of information, which are an integer key, which stores the value that of a certain node, and then we have 2 links, so whose type are list node, which are previous, and we call them previous and next. Okay, so here, as you can see that so this is the what we have in every node, and so here you can see that there are 2 special nodes. The first special node is the last one. This is the last node. For the last node, its next field is neo. So we use this one. We use this to denote neo. So because there is no node after it, so we assign a neo to its next field. Whereas for the head node, for the first node, because there is no node before it, so we assign a neo to its previous field. So its previous field is just a neo because there is nothing before it. So these are the two special nodes. So these are 2 special nodes in a linked list. Make sense?
Yeah, makes sense.
Okay. So this is what I just discussed. If for any node, if its next field is neo, it means that this node is the last one. If for node, if its previous field is neo, it means that this is the first node. Okay, so so here we are basically going to learn 3 functions called search and insertion and deletion. So search is like, say, suppose here we are giving a linked list. We're giving a linked list, whole linked list, and then we want to search for a value. Let's say k. K is, say, in this example, let's say set k as 4. So say we want to search for the node. Search basically return the node that holds k. Okay, we don't return the value, because if you search k, so if it just returns the value, then so if you search something, it will return something, then it does not make sense. So that's why we want to search for the node that holds the value that we are interested in. So here, suppose that you are giving a linked list L, and what you only know about this linked list is the head. Then how are you going to perform the search?
We would iterate through the list until you have.
Yes, great. So pretty much like what we discussed over here. Pretty much similar to what we discussed here. We start from the head, and then we slowly move head to the next, and we will stop the iteration or the visit until we find a node whose key matches k, the value that we want to search for, correct?
Yeah.
Okay, so if we want to write down the pseudocode, it will be something like So first we create a node X equal to the head of the L, and while X is not new, what we do is that we keep visit. We keep visit. So X equal to X dot next. So, but we will stop. We will break the loop if we find a X whose key is the same as K. Correct? So if X dot key equal K, we will break. We basically will break the iteration, and we will stop there immediately. Correct?
Understood.
Yep.
Yes, break means that you just terminate the while loop right over here. If you find a node whose key is the same as K, we just stop the search, and so that X will be the node that really stores the value that we want to search for. Correct? And
Yep.
finally, we just return X. Okay, so this is the pseudocode, and yes, so if you understand this piece of pseudocode, then let's look at the pseudocode provided in the textbook. So it has two parameters, L and K. X equal to so first we have X equal to the head, which is exactly the same as what we do over here, and then we have this line the same, but a little bit different is this: while X is not new and X dot key is not K. So basically, this is equivalent to this. They are just equivalent. So this means that whenever you see a X whose key is the same as K, we terminate the loop. The same as what we want to do over here, right? Basically, these two pseudocode are equivalent to each other. Both of them can find the value that will the node that holds the value that we are interested in.
Understood.
Mm-hmm. Okay, so if we go over, use this example, go over it. So first we have X as the head of the linked list, and then we're going to compare the key with the key of so of course X is not new, and then we're going to check the second condition if X dot key matches K, which is 4. No, it doesn't match. So it doesn't match. So what we do is that we will have X equal to X dot next. So we basically move X to the node after it. So and then X. So we go back to the while loop, and X is not new and its key is not the same as K. So then we move it again. And then we just, so right over here we have X, then we have X right over here, and then we're going to check if X is new or not. It's not new, and then we're going to compare the key at X with K. We find that okay, this is going to be false because they match. So then we terminate the while loop, and then we just return X, which holds the value 4 that we want to search.
So is like dot key like a built-in function for like a linked list, or you have to like create that yourself?
So sorry, I don't quite hear the first part of the question.
So you see how it says like if dot key. So is it the dot key function, like is it built in the linked list, or you have to create it yourself?
Okay, so the dot key function is not a part of the linked list. Actually, so let me terminate my presentation and come back to my to Eclipse. Okay, so here, okay, so let's come back to Eclipse. So if you look at here, every list node has 3 fields: key, previous, and next. So because X is a list node, the type of X is a list node. Here, so let me go to So because the type of X is a list node, so basically you can visit its key, its next, and its previous with the dot operator. So you're basically visiting the attributes of an object. Make sense?
Okay. Yeah. Thank you.
So we don't have to write that function, and as long as you have the definition of list node, it will work. Okay, so here, let me ask you. So any question with the search function of linked list? No? Okay, so then I'm going to ask you one question, okay? So guess what is the complexity of the search in linked list? Suppose that we have n nodes in a linked list. So in the worst case, how many nodes are we going to visit?
The O of n?
Yes. In the worst case, we are going to go over every node in the linked list to find the value that we want to search for. If the value does not exist in the linked list, we definitely have to reach the end and say, okay, we don't find it. So so the time complexity is O(n), because in the worst case, we have to go over n nodes. Make sense?
Makes sense.
Yeah.
Okay, sure. So then let's look at the insertion function of linked list. So here, if we have a linked list and we have so we have a node X. X is the type of X is list node. Okay, so the type of X is is a node. So basically, we want to insert a new node X into the linked list. So we always insert it into the beginning of the linked list. We always insert it into the beginning. Okay, so let's see how does the insertion process work. So suppose here we have a node X. We have a node X who holds the value, let's say 25, and its previous and the next field are both nil, because this is a single node. It does not have any connection with other node. So and then let's say we want to insert it into this linked list over here. Okay, so we want to insert it into this linked list. So this is X, and what we do is that first we have X equal to, we assign X to we assign the head of the linked list to X dot next. So this is like this. Okay, we are overriding the next field of X, and so give it a link to the first node in the original linked list. Make sense? So basically, we are assigning the original head, the head of the original linked list to the next field of the new node X. So it's like you're telling X. So now after you, it is the head of the linked list.
Is there a different function for if you wanted to change the elements of like a different node?
No, you need to do it in this way.
Okay.
Because basically you are overriding the attributes of an object. So this is the way to do that. As long as that object, or as long as that class member's type is public. So you're free to refer to that attribute with the dot operator.
So you're replacing the value, right?
Yes.
Okay.
Okay, and then let's continue. Okay, if the x dot head is not nil, so the head is not nil, the head is over here, is not nil. We have x dot head dot previous equal to x. Wow. So we assign x to the previous field of the head. So this is like originally this previous field is nil, but now we give it a new value. Okay, now before you it is x. Before you it is x, which is right over here. And then we have this, we have x dot head equal to x. So it's like we are assigning a new head to the linked list. Say that, okay, the head is the new linked list starts right over here. And then, so this is gone. And then, so we have, okay, x dot previous equal to nil. We basically assign nil over here. Originally it's already nil. So we just want to double, so make sure it is nil. And then this finishes the insertion. So let's say after the insertion, what we have is pretty much like this, something at the bottom. So we have the head pointed to the new node x, which holds the value 25. And then after x, it is the node 9, which was the node that holds the value 9, which was the head of the linked list before the insertion. So yes, in this way we finish the insertion. We basically insert a new node x into the front of the linked list.
Just one quick question, if I may.
Sure.
I think maybe I missed it, but why does it say L dot head dot previous equals x as opposed to like the next one?
Okay, so x dot head dot previous equal to next. So before we do this, we have L dot head point to here, right? So this is the head.
Right.
This is the head. So originally the head, the previous field of the head is nil because it means that there is no node before it. So it has to be nil, right? So now we're saying that because we're inserting a node before you, so you're not the head anymore, and you really should have someone before you. So the one before you is the new node that we want to insert, which is x. So
okay.
then
okay.
yes, we assign x as the left field, as the previous field of the previous head.
Mm-hmm. No, understood. Thank you.
Okay. Any other question? No. I know this sounds a little bit, say, very abstract. It's quite different from array, where when we do the operations, we know, okay, we're just playing the index, but here we're playing the address. So the one thing that you need to know is that in Java, so suppose here you create list node x, you create a new list node x. So do you know what kind of value does x hold? Actually you create x. So here, so if you say x, if you ask for x, it x. So this is the node that we just created in the memory. This is in your memory. X basically stores the address of the object in the memory. So it tells you, okay, by referring to x, you know where is this object located in your memory. So x is basically the starting address of the object in memory. So if you learn something like C or C++, you should have a very good understanding about it, because in C and C++ they support pointers. But in Java, we don't talk about this very often in order to reduce the level of difficulty. Here, so if you are confused about, okay, how can we assign x to some field? How can we assign an object to the field of some other object? So then you need to think about it. You can think about it in this way. So you're just telling the address of x of this object to a different object. So it's like it's something like after you buy a house, you tell your friends, okay, this is my address, this is my new address. Okay, so so here, so let's say how many operations, how many instructions do we perform in the insertion function?
Three, maybe. It depends on the if
one,
it's true.
2, 3, 4, 5. If it's true, in the worst case, it's so if it's true, then in the worst case, it is 5 operations, right? So we do a value assignment, check, equality check, assignment. So in total, 5 operations. So meaning that no matter how long is the linked list, in order for us to insert a new node, the complexity is just constant. So we got O1 complexity over here, right?
Yes.
Yeah.
Okay, so the insertion complexity of linked list is the same as that of the stack and queue. So then let's look at the last function that we want to discuss in linked list is delete. So we want to, what if we want to remove a node? So here we got a linked list L, and x dot, a node x. So here let's take this as an example. Suppose, okay, we want to, so this is the node x. We want to remove this node x from the whole linked list. Let's say what kind of operations do we perform? So first we check if its previous is new or not. So so here we can say that its previous is not new. Its previous basically hosts this node. So let's say x dot, this is x dot previous basically stores the address of this object, right? And then x dot next basically stores the object, the address of this node. Okay, so here, if x dot previous is not new, x dot previous is not new, it's this node, and what we do is that, okay, we let, so this is really tricky. Okay, we have x dot next, we will assign x dot next to x dot previous dot next. So we have x dot previous over here. So we give it, so this is its next field. We give its next field a new value, which is this node. Okay, the node after x. So this is like we are breaking this link and sending a new link from the node before x to the node after it. Am I correct?
Yes.
Yeah.
Okay.
But how do you actually delete the node, like the 4?
We don't need to delete the node. Remember that in the stack or the queue example, if we want to remove an element, we don't really remove it. Instead, we just ignore it, skip that.
Oh, okay. All right, gotcha.
Okay. So similar here. Okay. So let me repeat that because this is relatively, this is a little bit difficult to understand. So here we got x dot previous here, x dot next over here. So what we want to do is that we want to assign x dot next to the next field of x dot previous. Okay, we need to take this in a whole part. So x dot previous is here. Its next field is basically here. So we are giving its next field a new value. So originally x dot previous dot next is x, but now we say, okay, you don't point to, after you is not x anymore. It's not x anymore. After you, it is the one after x. Okay. So so this is what we do with this operation. And next, so we can just ignore the else part, and then we go to, because so we just executed the if, and then we go to the other if statement. If x dot next is not new, x dot next is here, is not new, x dot next dot previous equal to x dot previous. So we have x dot previous as over here. So basically you are telling, and we have x dot next dot previous. If we take this import. Okay, basically you are telling the person which is on the right of X, saying that okay, so now your left neighbor is not X anymore. It is the one to the left of X. Okay, so what we do with this is that we're breaking this. We're just give it a new link. Okay, go from, so we are assigning X dot previous to the previous field of X next. So we modify the link to here. Okay, make sense?
Yeah.
Okay,
Yeah.
this is pretty much like the previous operation that we did. So, and then it seems that we finished the deletion, but how? Let's go over it. Okay, so here, if you are asked to go over all the elements in the linked list, so basically you need to start from the beginning. Okay, so we start from head, and then we follow the link. Follow the link, we go this way, and then follow this link, we go this way. And if we want to go from the end to the beginning, come to the beginning from the end, following the previous link. By following the previous link, we go this way, and then this way, and then this way, and then we come back to the head. So here, as you can see again, when we want to delete a node from the linked list, we don't physically remove this node. We just skip it in a whole linked list. We basically only delete it from the linked list, but this node still exists. It's just separated from the linked list. Make sense?
Yes.
Yeah.
Cool. So this is these are the operations to remove a node from linked list. And here, what we can so here, let's just double check the number of operations. So if, let's say 1, 2, so it's like, if it's true, we're going to execute this operation. Otherwise, we are going to execute this operation. So in total, here we got two operations. And then here we got one equality check and another one. So at least, at most 2 operations. So in total, we got 4 operations. We need to perform 4 operations, at most 4 operations, in order to remove an element, a node from a linked list. So again, we can say that the complexity of deletion in linked list is also O1, because it is irrelevant to the length or to the number of nodes inside the whole linked list. Right?
Yeah.
Right.
Okay. So any question with the deletion function for linked list?
No.
Okay. So then here, let me briefly summarize the linked list data structure that we learned today. So in linked list, so basically it consists of listed nodes scattered. So this listed nodes are scattered in different locations of our memory. And then we learned 3 functions: search, insertion, and deletion. So the search complexity is O(n), because in the worst case, we need to go over every node in the linked list. Whereas for insertion and deletion, it is O(1), the same as stack and queue. Okay, so this is what we need to learn about linked list. Okay, so and then after this one, you are going to have your homework 4. So here, when you are doing homework 4, one difference is that, so in the pseudocode, okay, in the pseudocode, it's, so if in the insertion function, X is a node that we want to insert, right? X is a node. But here in the skeleton code that I provide to you, so let me stop over here and then come back to the my laptop. In the skeleton code that I provide to you, yes, here you can see that X is in the insertion function. X is a integer. So I have the node for node x is a integer value rather than a list node. So before you follow the pseudocode, you need to create a list node which holds the value x. And then after that, everything is the same. Okay, so pay some attention over here. So I intentionally do this because I want you to have a good understanding of list node. So that's why. Okay, so that's all I want to present for today. Do you have any question for me?
No, thank you.
Okay.
That homework's going to be due on next Friday, correct?
Yes, next Friday.
Okay, and that's also including the stack and queue.
Yes. I mean, this homework it's not going to take you too long because it's not very difficult. So I think most students can finish around 2 hours.
Okay, thank you.
Okay.
Thank you very much, Professor.
Thank you. Yes, have a good weekend.
You too.
Have a good weekend, Professor.
Yeah. Have a good weekend.
Thank you.
Professor. Hello. Okay, never mind. Professor, can I ask a question? I am Mahmoud.